Okay, welcome back. Made a couple mistakes there, and so I think this is video number 3, but we'll see how this, hopefully I get there this time. Okay, first question here says we've got this piecewise defined function, and that's one of those things that my joke is your spidey sense should go up because they're frequently really discontinuous, nasty little things. So we are going to try to find a value of k that perfectly makes this thing continuous. So right off the bat, in order for it to be continuous at 5, the limit as you approach 5 from the left better be the same as the limit as you approach 5 from the right. So notice here I have the limit as x approaches 5 from the left. I want it to be the same as the limit as I approach 5 from the right. And that should in fact be the same as the limit as you approach 5 itself. So when I did that problem, I noticed that as I got really close to the number 5 from the left, I got 5 minus 1 under a root, which gave me 2. But 5 from the right is this guy right here. 5 squared is 25. So from the right side, it looks like 25k. Now, obviously, I could say g of 5 is 25k itself, but that's kind of pointless to write that down because it's just attached to the same equation here. Well, again, so if this is to be true, that means 2 and 25k have to be the same, which makes k 2 25ths. So that's what I wrote right up here. If I could plug in 2 25ths for k, I would have a nice, perfect continuous function. Now, the second part is kind of important because it says, let's go ahead and sketch that graph. But again, I'm going to sketch the graph using k to be 2 25ths to make that, in fact, a continuous function. So right off the bat, 2x squared should be a nice, simple parabola. So notice my parabola extends to infinity to the left, but it stops at the number 2 because it says this parabola ceases to exist at 2. But if we plugged in 2 or got infinitely close to 2, we get really super close to the number 8. So I have an open circle right here at 2, 8. Now, once 2 hits, the square root here, 2 minus 1 is 1. So if you plug in 2 to this, you get 1. So it starts a square root journey at 2, 1 up until we reach 5, 2. So remember, square roots have this kind of shape, but we only have a little piece of it, at which point in time at 5, 2, because we made the number here match this. So at 5, as you get close to 5, the answer is supposed to be 2, and then it becomes a nice little part of a parabola from here on out. And you'll notice it's a pretty nice little simple parabola that's pretty gradual because, of course, the leading coefficient is 2 25ths. But once we have that, it makes the picture pretty easy because as I approach 2 from the right, it gets close to 1. As I approach 2 from the left, it gets close to 8. But since those two numbers are not the same as each other, I have to say does not exist for the limit as x goes to 2 without any kind of qualifier. Now, moving down here, we made the function continuous at 5, so all 3 of these values had to be the same. And since the first answer was 2, then the rest of them had to be, in fact, 2. So coming down to the next problem, keeping in mind our little strategy that we keep using. Let me move this up a little bit. The first thing we're going to do is we're going to plug in the number 2. Now, again, it says 2 plus, but we're just going to be greedy and just plug in the number 2. And if I plug in 2, I get 12 plus 4 minus 8, which 12 plus 4 minus 8 is not 0. 2 plus 1 is also not 0. I get this information, and I got a simple 8 on top and a 3 on the bottom. And since I didn't get 0 over 0, I'm just done. Easy peasy, done. Moving on. Same idea on this one, but since I'm going to infinity, all I had to do is compare the relative powers. And since the leading coefficient on top is 1x to the 5th, and I have negative 9x to the 5th, it's just the ratio of those leading coefficients, and therefore I get negative 1/9. That would be our end behavior asymptote. It's also our limit. It's also the equation of a horizontal asymptote, all these different ways of saying the same information. Okay, coming down to the next one. So this is, again, one of those things that we kind of call Señor Salta. It's got that little jump. Again, what we'd like to say is that 3x over 2x would be 3/2, and in general, that's true. But as you extend to the right, the numerator and denominator would be the same signs. They're both positive. But as you go to the left, the top stays negative, but the bottom, because of that absolute value, is going to go positive. So we're going to get -3/2. Okay, so moving on to the next one, a little bit of a reminder that sine x over x is always 1. That's actually known as the squeeze theorem, a pretty important theorem of calc. So when we go into here and we look at this thing, the first thing I did is I decided to break up the sine squared of 4x as the sine of 4x times the sine of 4x. Now that's pretty nice. That works pretty well. I went ahead and I decided to give the two x's to the bottom. I threw the 5 in front. So notice that if we kind of hold it up like this, we have the sine squared of 4x over x squared. But I needed a 4 in both of these holes to make the two pieces match, and so I decided to put a 16 in front. The 5 down here is just because one of the properties of limits is you can bring that number in front. But now we're in a nice little situation where you have 16/5 times the product of these two limits, but each limit is the number 1. So of course 16/5 times 1 times another 1 is just going to be 16/5. And then our final question, which again I think we did in class, so you guys probably do not need it. But if we take the limit as you approach -1 from both the left and the right, you get a minus 1 on the top one and negative b plus 4. And again, there's nothing fancy about that. I literally plugged -1 into the top equation, got this. Plugged in -1 to the bottom equation and got that. Now that gave me a pretty simple little equation that a minus 1 and negative b plus 4 have to be the same because rho in equals rho out. It's not very good. I don't have enough information to really finish. But then I went a little further and I said, well, let's take a look at what happens around 3. Well, as I approach 3 from the left, I get 3b plus 4. Again, just plugging 3 in here. But when I plug in 3 here, I get, hey, what do you know? I get a really nice answer, which means 3b plus 4 has to be identically -1. So I put that right here. 3b plus 4 has to be identically -1. So if you kept going, 3b would be -5. I just brought the 4 across and divided. And since I had this equation up here, I did just a very small amount of manipulation, and I just took the negative b that was here and I replaced it with -5/3 and just did some very, very simplistic simplification, added the 4 with the 5/3, moved the 1 across, and I ended up a being 20/3. I'm hoping that's the last time I do this video. So hope that's helpful. And that it didn't go too fast because I was using what I'd already written down. Okay, bye-bye.